Wonderful Science Sunday. Good to see you, Mary. Glad you could make it. Escaped the chaos of the children.
Yes.
Yeah. Glad you could all make it. We really appreciate the church providing us this space and a community of people who like to hear about scientific facts and theories and reality. And I'm privileged to be the leader of the local humanist group as well. Humanists have a philosophical disposition, a metaphysical disposition, such that we are not persuaded that magic is real in the universe. It would be cool if it were. Think of all the possibilities. But, you know, even with reality and chemistry and physics and astrophysics, we can do a lot with the stuff that we have available. It's well nigh magical. So we appreciate the church. We've been doing this, Mike and I. Mike's been doing it, I think, 16, 17 years. I'm 1 year less than Mike. I came on board the second year of Science Sunday, and it's really been a great source of enrichment to my life and the lives of, I hope, you, and many of you have been able to give presentations as well. I see several faces in here that have been up here talking about scientific facts and fictions, pointing out the fictions, not trying to convince us of fictional things. Unless it's Joanne, who's written fiction books, 11 of them. So if you're interested in fantasy books, like Tolkien kind of books, you can talk to Joanne. She can tell you about her books. And welcome to another Science Sunday. So, she did not pay me. Yeah, yeah, that was a free advertisement. All right, today I want to talk about science that some of these scientific claims may be things that you get wrong, or things that you learned in your educational history that have since been amended. And want to talk about things that we may be mistaken about in terms of our scientific claims. And then at the end, I want to draw a little bit of a lesson from that. As I said a couple of Science Sundays ago, one of my approaches this year, one of the things I'm going to do deliberately, is to try and make sure that each presentation I give is associated with some kind of normative message. So positivist, from a philosophical perspective, a positivist claim is a claim about what's real and true. A normative claim is a claim about behavior, what ought to be true, what the world ought to look like, how things ought to be. And it entails things like morality and ethics and approach to questions and whatnot. So I'm trying to combine a lot of positivists sort of information with the normative opinion that I provide. All right, misconception number one. How many of you learned that we use 10% of our brains? Excellent. It was a very common misconception that was taught throughout the 70s and 80s, 50s, 60s, etc. And I believe it originated from a study that was done before the age of what we would consider modern brain scan technology. And the study, you know, the scientists tried to be as diligent and accurate as they could, but they came to some conclusions that proved to be mistaken. So what's the truth as we know it today? We use all of our brain, but not necessarily at the same time. So you've heard that we have a lobe in our brain for vision. We have parts of our brain that are dedicated to helping us form memory, like the hippocampus. We have frontal lobes and parietal lobes and occipital lobes and so on and so forth. And then different regions in the brain, Broca's region and whatnot. And the brain acts like a series of interconnected networks. We might even say today, with the way we approach information and knowledge and computing, It's a series of interconnected neural networks. And we've borrowed that term, neural network, from the way the brain is organized. And so the brain is a bunch of interconnected networks down to an individual neuron has network-like capabilities entailed in a single cell about distributing information, processing information, making inputs and outputs. So it's a continuous scaling of different scales or sizes of networks. And not all of the network is active at the same time, or you would get chaos or nothing, right? Imagine if every memory cell and every possible operation in a desktop computer or a laptop computer were active at the same time. It would just be nonsense, right? So also, evolution tends not to build things in excess of what is prudent for survival and reproduction. And so the notion that we would carry around 90% of metabolically expensive tissue that is unused is hard to swallow, let's say, right? We don't have any evidence that evolution organizes things in such a way to be that wasteful. One of the other things we've learned about brains and their organization is that in the mid to late teens up into your early 20s, neurons are pruned. So the count of the number of neurons in your brain that you're born with is diminished over time. And I think that's consistent. I've talked a little bit about neural networks and how they're used in artificial intelligence. I don't want to get into that again today necessarily, but there's a similar concept even in computer science in the way we train neural networks, that some connections are reinforced and others are deprecated, to the point where in a brain, some of the actual neurons are pruned. They are withered and reabsorbed. So if you don't use it, you lose it. So if you had 90% of your brain that was unused, nature would repurpose that material, plausibly. Right. The myth is from the early 20th century. There was a disconnection between neurons or a distinction between neurons and astrocytes and other cells in the brain. And when this myth was first, or when this claim was first put forward, that distinction between ganglia cells and neurons and astrocytes and other cells in the brain, that distinction was not recognized. And so there are many, many cells in the brain that are not implicated in information processing. Although I think recently astrocytes have been, there's some speculation that astrocyte cells, which are kind of the scaffolding on which neurons are knitted into, if you will, woven into. There's some claims made recently that astrocytes may have a role to play in information processing as well. So we continue to learn more. All right, brain myth number 2. How many of you have heard about the amygdala and it being implicated as the center of fight or flight response in the brain? Right? I learned that in psychology in, I don't know, high school or college. The amygdala says, run, hide, fight. Right? It's primarily, the way I learned it, it's implicated in fear responses and threat responses. And we actually have 2 amygdalae, and there's one in each half of the brain, and they're little almond-shaped regions of the brain, of the limbic part of the brain. It's an ancient part of the brain, relatively speaking, in terms of evolutionary history. And these are kind of almond-shaped. In fact, that's where amygdala comes from. The word amygdala comes from the fact that they're almond-shaped. All right. It is incorrect. Right? So if you've learned that and you haven't updated your store of information about the way the brain works, you have been making a mistake. It is not a flight or fight center. Instead, it's more accurately described as a novelty processing unit. So any kind of novel stimuli. The amygdala is more accurately understood as a salience detector, right? How relevant is this to me? Is it relevant? Is it novel? Could be something pleasantly novel. You know, looking at the Grand Canyon for the first time with your own eyes, right? The amygdala is activated. So it is activated during stress and potentially threatening circumstances, but that's by far not the limit of its activation profile. So it's not the fight or flight center of the brain. In fact, fight or flight activates many regions of the brain, right? There's adrenaline that's released, there's your respiration and heart rate change in response to adrenaline. There's several glands and regions of the brain that are implicated in the decision processes we make or the reflexive actions our bodies perform when we perceive a threat. All right.
A question.
Yeah.
What does it do once it figures out that there is a surprise? It's sort of like an airplane warden saying they're incoming, they're incoming. What happens when it goes alert?
Yeah, so it's connected to other regions of the brain, and depending upon whether it's a threat or a delight or an enticement, etc., it then cascades processing further into the brain to try and form a new memory or activate existing memories or, if you encounter a field of beautiful flowers, one of your first things you may do is inhale, try to smell them, right? So anything surprising, noteworthy in your environment that gets your attention, your salience processor then cascades attention, right? Pay attention to this, attend to this, to other parts of the brain. Okay. Another myth. Oh, wait, maybe it's not a myth. Maybe it's absolutely true. Maybe I threw in a red herring here. How many of you have heard that we share 98.8%? Maybe you've heard 98.6, 98.7. How many of you have heard we share 98.8% of our genetics with chimpanzees? Excellent. This is still often talked about using exactly these terms. We share 98.8% of our genetics with chimps. Well, kind of depends. So it's only true if you ignore insertions, deletions, duplications, chromosomal rearrangements. Essentially, if you only count the parts that are easy to compare. It's like looking at alphabet soup and saying the letters in this soup are the same as the letters in the other soup. But you can do different things with those letters. Right? You can spell out different words. Mommy, I'm hungry. I don't want to go to school. Right? You can do different things with the context in which those codons are expressed. And the context of our genetic profile is massively important. It used to be, when I was in school back in the 80s, it used to be that there was this whole massive component of DNA called junk DNA. It's not so junky, right? It controls where, when, and by how much a particular gene is expressed. Now, this study that found 98.8% similarity included a lot of genetic material, a lot of base pairs distributed throughout the genome, but it didn't necessarily specify the ordering, the sequencing of those base pairs and the implication of slightly different sequencing. So if you look at it more holistically in terms of the genome and its effect on the phenotype, so your genotype is your chromosomes and your DNA, and your phenotype is the organism that results from expressing those genes. When you include the full picture, the divergence is at least 4 to 6%, possibly as high as 10, I even read in one paper, 12%. So that's the difference between 98.8% or 99% similarity and 90% similarity, right? So it's context dependent. And that's one of the lessons to take about claims for scientific facts. A lot of times, context is king. What do you mean? In which context are you making this assertion? What are you measuring? How are you measuring it? These are the details that win people Nobel Prizes when they find some relevant context that can be changed to lead to some new insight. All right. Speaking of genetic similarity, I thought it'd be fun to throw this in. So this shows the same sort of similarity count between a typical human genome and other living things on Earth. Archaea, very ancient lineage of single-celled organisms. We share only about 1% of our genetic material with Archaea. But if you get to something really complicated and highly organized and incredible, like a yeast cell, well, we share 30% of our genome with a yeast cell. We share about 25% with a bee. Bees have had a long time to evolve, and so they've evolved some fairly different genetics compared to us. And even the commonality between us and yeast and bees is a little different. Bees have been on a different evolutionary path for 500 million years or 600 million years. Fish. Your genes are about 70% fish. Well, yeah, you should be suspicious. Validate. This is just me, right? I mean, I'm putting numbers up here. Maybe you should go validate them if you're interested in the topic. We share about, what is that, 85 to 88% of our genetics with a horse. And of course, somewhere between 90 and 99%, essentially, with a chimp, depending on how you measure it. But that same caveat, depending on how you measure it, applies to all these other things as well. All right. Well, this is a picture of what? Mount Everest. What is Everest?
Second tallest mountain.
Excellent. Aha. So this gentleman added an important caveat that makes his statement much more precise and accurate. It is the highest elevation above sea level. If you just say it's the tallest mountain, right? I'm going to show you why. This is Mauna Kea in Hawaii. And in this image, which I ripped off the internet without attribution, I apologize. But you can see the green part above the water, and then this huge, massive amount of mountain underwater. If you compare it from base on the seafloor to the tippy tops where the observatories are in the clouds, then it's taller than Mount Everest. So is this the tallest mountain on Earth? Right? All right, let's go to the next one. Mount Denali. This has a similar context to justify it being ranked as the tallest, as does Mauna Kea. From the lowlands to its peak, it sits in a relatively flat, low part of a piece of land. And if you were to start off on the low part of the land, 4 miles away, 5 miles away from the peak, you would have the largest number of steps to go from the bottom to the top of this mountain. It is the longest climb in altitude that you would make trying to perambulate your way up to the peak. If you have to take the largest number of steps to get up there, maybe it's the tallest mountain on the surface of the earth. Right?
Maybe it's just the widest.
Maybe the widest. Or did you say widest or wide? Wide?
How wide is it?
I don't know. I came across, and I don't remember the name, and I didn't put it in my slides, but I did come across a mountain that had the greatest bulk. So it's, if you were to add up its total mass, it would be the most massive mountain on Earth. And I don't remember anything except I saw that. I don't remember where it is or what it's called.
Mount Obesity.
Yeah. Mount Ho 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 Ho. All right. So you can assert with some justification that this is the tallest mountain on Earth in terms of the number of steps it would take to climb it. Ecuador has some really interesting mountains. One of them is Chimborazo. I don't know if I said that right. It felt good to me. It's only 20,500 and some feet above sea level as opposed to Everest's 29,000. So it's a couple of miles less lofty compared to sea level. But its peak is 3,968 miles from the center of the Earth. It beats Everest by 1 mile. Our Earth is kind of squished, right? It's got angular momentum. It squishes it a little bit. So we have it's called an oblate spheroid. And because the Earth is an oblate spheroid, a mountain close to the equator in a country like Ecuador, see what they did there? Can reasonably claim to be the tallest mountain on Earth in terms of its distance from its peak to the center of the Earth. Like I said, it beats out Everest by a whole mile. Also in Ecuador is Cayambe. This has the distinction of being the furthest summit from the Earth's axis that runs from the north geometric pole to the south geometric pole, the axis of rotation of the Earth. This is the mountain that has a peak furthest away from that axis of rotation. Right? It's another way to say what is the tallest mountain. Here's a diagram displaying some of that. So the Earth is kind of tilted 23 or so degrees, right? You know the Earth tilts on its axis, and then you see the equator there as the red line. And then schematically, these are not to scale, schematically represented is Everest, which is way up towards the, relatively speaking, closer to the pole, the North Pole. Mauna Kea is closer to the equator, but Cayambe sits essentially right on the equator. It is the only place on Earth that has snow all year round at the equator. Another interesting factoid. And you see there that because it's aligned with the equator, also positioned on the Earth's bulge, it ends up being the furthest from the Earth's axis. It's a little closer to the equator than Chimborazo. Another way to denote the tallest mountain on Earth. Kilimanjaro in Africa. In terms of being an isolated, prominent mountain with no other mountains around it, to give you a sense of scale and spectacle and awe, we have this giraffe. Oh, and behind it is a mountain. So this is possibly considered the tallest mountain on Earth in terms of its psychological effect, in terms of its relative height compared to its surrounding terrain. Right? Even Denali in Alaska is part of a small mountain range. This is all by itself. So, very impressive. Speaking of impressive, I didn't know about this mountain until I started researching this topic, Nanga Parbat in Pakistan. The name means naked mountain, largely from what I read, because its sides, at least this side of it that we're looking at here, is so steep that it doesn't get much, relatively speaking, much snow accumulation, not much glaciation and whatnot. So you see a lot of bare rock. This mountain, if you stand on this flat plain or near this flat plain and look up, it is 2.86 miles straight up. It's essentially a cliff face that's nearly 3 miles tall. That is impressive.
Is that a cirque?
A what?
A cirque?
A cirque?
Yeah, the starts of a glacier.
Oh,
Is that how it was formed?
I don't know. The Himalayas were not formed through glaciation. I don't know if the cliffside was carved out by a glacier.
Okay.
I'm sorry. That's a word I didn't know. Cirque?
Yeah.
It's the mountain that's the start of the glacier?
Yeah, it's a bowl,
Okay.
typically, and it's in the side of a mountain chain. It's where the glacial, where all snow packs in, and the glacier forms from that flowing downhill.
Oh, thank you, Joanne.
Oh, that was a Phyllis.
Oh, well, thank you, Phyllis. Yep. Learn something new every day. Whether I remember it or not is a whole different story. Right, so this is only the 9th tallest mountain in terms of its summit with respect to sea level, but it is perhaps the most awesome mountain spectacle available on Earth. And schematically, you know Half Dome in Yosemite National Park? This is a diagram showing Half Dome in relation to Nanga Parbat. Half Dome is very impressive. You can stand at the foot of Half Dome and you will probably be awed. A-W-E, not O-D. Well, you'll probably be that too. So, very impressive mountain. All right. Now, let's move on to some cosmological scientific claims that you may have integrated into your corpus of knowledge about the way the universe works that you may be mistaken about. This is so how many of you have heard that black holes evaporate? Okay, handful of you. Black holes evaporate. There you go. That's, as far as we know, that is a true statement about nature. Sort of. Okay, we've got some caveats to mix in here. Stephen Hawking wrote a very a best-selling science book called A Brief History of Time. In my opinion, the book is crap. It's a very good book. There for the YouTube audience. So in that, I find it to be difficult to parse, and some of the explanations are problematic. But Stephen Hawking worked mostly in mathematics, not in words. He was a mathematical wunderkind. And I do not want to detract from his absolute genius, right? He was very interested in the realm where Einstein's theory of gravity and general relativity would bump up against phenomena related to quantum mechanics. And perhaps the most vivid example of that in the known universe is a black hole. I'm not going to talk much about black holes specifically, but one of the conclusions he came to mathematically was that black holes, in a very real sense, are like it's called a black body in physics. In physics, there's this notion if you have something completely black, it'll emit a heat signature across a spectrum of light. And that black body radiation, if you take a brick and throw it in a fire, first it's red hot, then it's white hot, right? And the peak color, whether it's in the red part of the spectrum or the blue part for white hot, that peak is described by a mathematical law. And it turns out if you combine some of the theories of quantum mechanics and relativity, you can find that a black hole has a black body kind of temperature associated with it. Not in the red part of the spectrum, not in the blue part of the spectrum, in the very, very, very cold part of the spectrum for typical astronomical black holes. Now, there's been speculation for decades about something called mini black holes. There has never been any evidence of these found in nature or in a laboratory. There was some speculation that CERN, when it was activated, might create a mini black hole in the laboratory, et cetera, et cetera. Mini black holes, as far as scientific observation has been able to determine, mini black holes, micro black holes, don't exist. However, gigantic black holes in the centers of galaxies, stellar mass black holes from a collapsed massive star, those we can say with great confidence do exist. And we can solve the equation to see how hot they are. And I'll tell you the result in a minute. But one of the things Stephen Hawking talks about in his book is this idea of where does the heat come from? And he says, well, one of the ways you can imagine it is you've got a positive particle and an antimatter particle, and the space is like a froth. In quantum mechanics, one of the ways you can treat empty space is as a kind of a messy froth, like the old analog television, and you'd tune it to no station at all, and you'd see this froth of white and black dots. Well, one of the ways that you can characterize empty space, devoid of matter and energy, in quantum mechanics, is to ascribe to it a certain amount of this frothiness. And these can be accurately labeled as virtual particles, that's a whole other topic. Some scientists say that they are nothing other than a calculation shortcut. Others say that there's some utility in thinking about them as a real property of empty space. Anyway, Stephen Hawking in his book said, you've got this virtual particle, and they always come in pairs because you got to balance out certain quantum numbers, like charge has to add up to 0 and spin has to add up to 0 and whatnot. So virtual particles always manifest in a pair as a positive matter particle and an antimatter analog. And in his book, he says one of those pair gets eaten by the black hole because it's just a little tiny bit inside the horizon, and the other one's like, whoo, I made it out of here, and goes, woo, flying off into the universe as a piece of matter. Well, there's some problems with that. First of all, where does the piece of matter that escapes get enough kinetic energy to escape the gravitational pull of the black hole? Secondly, if a piece of matter or antimatter falls into the black hole, that has matter and antimatter have energy. So that means you're adding energy to the black hole. So why would the black hole evaporate if it's swallowing particles all the time? Right? So those are a couple of the big problems with the picture that Stephen Hawking paints. However, his mathematics that describes the situation, it's just his prosaic explanation so that we lay people can visualize it, not the best. In fact, highly problematic. So we got a couple of questions or assertions.
Questions?
You said that the particles are always in pairs. Well, if one gets sucked into the heart of the black hole and one gets ejected out, now they're not in pairs anymore.
Right. Yeah, there's a whole question about entanglement and so on and so forth. That, yeah, there's reasons to be skeptical of that particular view.
So yeah, there's various problems with referring to these as the effect is a virtual particle thing. But one thing I was going to point out is, and sorry I came in late.
Welcome.
But,
Glad you're here.
one thing I was going to point out is I don't know if you've mentioned the cosmic microwave background at all yet.
I will get to that.
Yeah, which is like
I'm going to get to that.
yeah, and it turns out that that's
Yeah.
Well, maybe you were about to mention this. Yeah. Okay, sorry, didn't
Yeah.
mean to jump at it.
Yep. I know where you're going, and I'm going to be there too. All right. So instead, a better way to think of it is the following. First, pairs of particles aren't generated, nor is one trapped by the event horizon. Okay, I just covered that. It's just a bad model to keep in your head about how black holes evaporate. Thermal blackbody radiation, typically they're photons, not electrons or other matter constituents. They constitute the radiated energy until a black hole is about the mass of an asteroid. So imagine every black hole we know is at least 3 or 4 times more massive than the entire mass of our sun. Imagine how long it would have to just sort of radiate a low temperature into the cosmos to have radiated away enough mass energy that it only has the mass of an asteroid. Quintillions of septillions of years. And once you get a black hole that's about the mass of an asteroid, its temperature, its radiative temperature goes up in an exponential spike. And that's when you start getting visible light. So a black hole about the mass of an asteroid would start to emit visible light. Before that, the thermal radiation they emit is tiny and wimpy. So wimpy that I'm going to cover your point in just a second. The energy comes from the gravitational field. And a gravitational field is inextricably tied to the mass, actually the stress energy tensor. Energy is mass equals mc squared. So energy is mass, and then also you can have stresses within a region. Think about compressing a spring. You haven't changed its mass, but you're storing energy in it, right? So you can mathematically represent the total amount of energy of all forms in a region, and that total amount of energy is exactly associated with a specific amount of gravitational effect. So if energy is radiating away from the gravitational field, it means that energy is being removed from the gravitational force field. That's one way to look at it. And correspondingly, the mass of the black hole diminishes in exact proportion to the energy that it's radiated away. But the energy comes from the gravitational field and relativistic effects about an observer at a certain distance from a black hole versus an observer at infinity. They will see a different space-time context, which is something I'm going to delve into more in a minute. And it's that different context that gives rise to a measurement of an energy difference. It's a lot more subtle, but the mathematics remains the same. The mathematics that Hawking first formulated remains valid. It's just the explanation is a little more nuanced, and it doesn't give rise to some of these questions that make you go, but that doesn't make any sense, because it doesn't. All right. For an astronomical black hole made from a collapsed star or many collapsed stars to completely evaporate, it'll take something like 10 to the 68 to the 10 to the 103 years. That's a 1 with 68 zeros behind it, or a 1 with 103 zeros behind it. Every time you add a 0, you multiply it by 10. Not by 2, by 10. The universe is 10 to the 10th years old. We've added 10 zeros to the age of the universe in years. Multiply by that by 10, another 78 times. 10 times, and another 10 times, and another 10 times, and another 10 times, 78 more times, and you'll get to the era, the epoch of our universe's future, where black holes are significantly evaporative.
So I don't have to worry about it.
No, you don't. All right. However, no black hole in the known universe is currently evaporating. Not a single one. Do you want to tell us why?
Yeah, because, thanks. Because the cosmic microwave background, which is sort of the afterglow of the Big Bang, is the black body radiation spectrum for it is around a little under 3 Kelvin, 2.73 Kelvin, which is hotter than the radiation temperature of the black hole. So they're absorbing that faster than they're radiating away.
Right. So there is no such thing in our current universe as an evaporating black hole.
Oh, the other thing I was going to say, if I remember correctly, and you may remember this better, that it's the temperature, the effective temperature is inversely proportional to the surface area.
Mass. It's just mass.
It is proportional to the mass, but I thought, yeah.
Yeah.
Well, but the surface
But the
area is
surface
also
area is also proportional to the mass.
but yeah.
Right, yeah. Yep. All right. So speaking of cosmology, here's another thing. How many of you heard about the fact that light from faraway things is redshifted as it travels through space? Yep. Very popular on TV shows and in popular books about science. Light travels through space and it's like, woohoo, I'm free! And I don't know, after a few billion years, it's like, I'm free, but why does it matter? Right? So this idea is that old light that's traveled cosmological distances in our universe stretches as it moves. Nope, doesn't happen, right? There's a much more science fiction friendly way to view this. So here's the classic theory. You've got some distant galaxy, the bright spot up in the corner of the image, and it emits, I don't know, visible light, blue light. By the time it gets to the James Webb Space Telescope, it looks like a little red dot. In fact, there are things this James Webb Space Telescope has discovered that we call little red dots, right? And the James Webb Space Telescope was specifically engineered, largely its purpose is to look at things that are red and dim. Big mirrors because they're dim, infrared sensitivity because they're red or infrared. And that's because light-emitting objects in the early and distant universe have had their light red shifted? No, that's not the best way to think about it. Sorry for the small font. I'm usually better about that. Cosmological redshift happens because the photon was emitted when the universe had a different metric than the one in which we measure it. We aren't watching the light stretch. We're comparing clocks and rulers from two different versions of the universe. Now, doesn't that sound like science fiction?
It sounds hokum.
This is more accurate. What do I mean when I say the space-time metric? I mean, that's science fiction, right? No, it's the way Einstein's theory of general relativity characterizes the geometry of a region of space-time, and that geometry is four-dimensional. That includes x, y, and z, and the dimension of time. And if you start comparing different profiles of parcels of space-time, you will find that those metric units, meters and seconds, those units are different when you compare one region of space and time to another in some contexts. And one of the contexts in which this difference really shows up is between the early universe, when the universe was vastly smaller, it had a much more compressed metric, compared to today, when it's much more spread out. Well, the light didn't change, the measuring scales changed over time. Where we are. If we had been halfway to that little red dot, the light wouldn't look red, it would look bluish or greenish or yellowish. I don't know which. But that's because we would be comparing the space-time metric at that juncture of space-time with the space-time metric near the beginning of the universe. It's that comparison that would allow us to measure the light properties and see them as different than we expect. We know the color of light that hydrogen emits. Excited hydrogen emits a particular color of light, as does every other molecule in the atom. And we know how to measure that. But yet when we look out at the early universe, we see all of our preconceptions about the way hydrogen light works, we see all that shifted down in the spectrum to the infrared region or lower. And that's because we're comparing we're looking at a messenger from an earlier space-time. Oh, doesn't that sound like science fiction? It is a more nuanced but more accurate way to understand the cosmological redshift. Otherwise, you may end up asking questions like, well, where does the energy go? It starts as blue light, which has a lot more energy, and by the time it gets to me, it's red light. So why did the photon run out of oomph? Right? Where did the energy go? It's not.
Why isn't the energy just diluted? I mean, light behaves like a wave, depending on how you look at it, right? So if you're stretching out the space through which this light is traveling, the energy is just diluted.
But the photon doesn't get bigger or larger, right?
So?
Where does the energy go? Is it radiated away? It's already radiation.
It's where it's always been. It's just diluted.
Diluted how? In what form does the energy manifest? No, it doesn't. It doesn't work that way.
I have to disagree with you here. I would say that what's happening is that with the metric expansion in the universe, what's happening is it's not stretching as it travels, it's that the universe has stretched.
Correct.
Right? And we are, because light has a finite speed, we're seeing light emitted according to the same physics, except for the space-time metric, far away. And so, but for it to get to us, it has to travel through a expanding universe. And so space stretches. And so, yeah, the explanation is that for a unit volume of space, the energy density of the radiation stays the same, but because of the metric expansion, it's the same energy density in a larger volume.
Right.
So yeah, like you were saying, it's spread out.
Right.
And that's why it's lower energy photons.
Yeah, it's not a terrible argument. I think it's more, my personal opinion about it is that it's more insightful to think about it as a message from an earlier universe that had a different space-time metric, that was constituted differently in terms of the way measurements of time and space work compared to 13.8 billion years and light years more distant in space and time.
Is this not a direct measurement of the expansion of the universe?
Yeah, sure. It can allow us to characterize the expansion of the universe, which leads to the Hubble tension and a whole other things. All right. Next topic, the Big Bang. All right.
Boom.
We've seen television shows. I saw one where the Big Bang was this explosion, and out of this explosion came equations that hit you on the forehead. Equations like E equals mc squared, etc. Right? Famous equations in physics would splat you right in the forehead. You were somewhere out in space looking at this firework. That is manifestly an inaccurate characterization of the way the Big Bang worked. If you were, by some magic, able to exist as a biological and conscious entity at the time of the Big Bang, notice I didn't say the place of the Big Bang, at the time of the Big Bang, what you would see is a wall of light surrounding you. And over time, that wall of light would get further away and a little dimmer. Until 13.8 billion years later, if you look out at the universe, you'll see a wall of light still surrounding you, but it's microwave radiation that's 2.8 degrees Kelvin. We are in the center of the Big Bang. But so is the Andromeda Galaxy. And so is M87. And so is the little red dot that is at the edge of our observable universe. This is why the geometry of space-time can mess with your head. Every place in the universe was at the center of an explosively expanding space-time full of initially light. It's the best way to say it. And that light, eventually gamma ray photons and whatnot, decaying into particle pairs, etc. And eventually the universe expanded enough that there was enough space for the light to cool off, for the radiation to cool off enough that actual particles could come into existence and persist and not turn immediately back into light.
You were saying light. You mean they're actually photons, or is it just an energy which is something that we're not 100% sure what it looked like?
It depends on what epoch you're talking about. So the cosmic microwave background radiation is from what's called the surface of last scattering, about 380,000 years. If you extrapolate backwards in time and you assume a fairly linear smushing of the universe, the surface of last scattering in that linear extrapolation would have been emitted 380 million years after the Big Bang. Or is it 1,000? I think you're right. I think it is 1,000.
Yeah,
Yeah.
but that explains where all the energy went, right? It just expanded and all the energy was diluted. And the more the universe expands, the more diluted the initial amount of energy. You might ask, where did that initial energy come from before the Big Bang?
Oh, yeah, that's a great question, and we have no clue.
So we can make up anything we want, right?
Well, so that gets into the notion of scientific plausibility, right? First of all, we've got to apply the laws of nature as we know them to be manifest in our universe. Laws of nature don't allow for violations. They'd allow for things analogous to phase changes, where one set of laws or rules may take over in a domain of heat and temperature and particle density different than another set of laws of nature. But if we extrapolate responsibly, we can extrapolate back in time even prior to the surface of last scattering, the sphere of light that surrounds us, the remnant of the glow of the Big Bang. We can extrapolate back in time beyond that quite plausibly. So we can talk about when electrons came into being, and when protons came into being, and when hydrogen and helium and lithium came into being, and their relative abundances in the universe that we observe today. That we can do all kinds of that using our known laws of nature, the laws we've discovered and validated. But we reach a point where the laws that we're able to write down and comprehend are highly problematic at best. And we don't know. The universe could have existed in some physical state that we can't describe yet for eons, for eternity. Who knows? Nobody knows before what's called the hot Big Bang. So just prior to the hot Big Bang, the idea is that there was a brief period called inflation. That's speculative. It answers a bunch of riddles we see in the universe. I don't want to get into that today unless you want to stay for questions. But the other misconception about the Big Bang is it started from a singularity, a single infinitely dense nugget of energy. And from that, the Big Bang happened. We have no evidence. I'm not saying that is manifestly untrue. I'm saying we don't know. Nobody knows. There are speculations, scientific extrapolations and speculations consistent with that view of the origin of the universe, and there are many other speculations consistent with other views of the origin of the universe, the absolute origin. So if somebody tells you the universe started off as an infinitely dense speck of energy, they're not being honest about the best we know. The best we know is we don't. Right?
It's a definite maybe.
Right. Okay, it wasn't an explosion, etc. Prior to the cosmic background firewall, we have some to no idea what happened, depending on how far back behind that you go. All right, another misconception. Remember this? I was taught this. How many of you were taught this? It is wrong. Just absolutely wrong. Cockamamie. Taste cells are distributed all around your tongue, and all taste cells respond to a combination of these stimuli. You can taste everywhere on your tongue that you don't have nerve damage, etc. Wrong. Just wrong. All right. It arose from a 1901 German study. I mean, it's over 100 years old, this idea. And yet I found this in a modern depiction of fact. The lesson, always be willing to change your mind. How many of you changed your mind about something today? That's awesome! And you're old!
Yeah.
Wow! Double check your facts. Scientific knowledge changes. I make a distinction, and I make this explicit in my book, that scientific facts and laws are human efforts to capture, conceptualize, and communicate natural laws and natural facts. Nature is as nature is. We can represent that in words, like Stephen Hawking tried badly to do when he tried to explain the evaporation of black holes. He tried to represent that natural fact and phenomena in English words, and he didn't do a great job. But his mathematical representation of that was delightful. And science can be thought of as a journey of the human species to make ever more accurate models and claims about natural facts and natural laws. Once again, I invoke this diagram from my book that I've shown in many of my presentations, which is scientific knowledge. We are on a journey towards an asymptotic, there's that word again, asymptote, it's got a P in it, asymptote, an asymptotic journey toward a perfect characterization of the facts of nature. In some regions, we're far from it. In other regions, we're close to it. That is all I have for today.
And we have people waiting to use the room.
All right. Thank you.